No, Abhishek, is your turn.
Um, thank you for the introduction. So today I will be talking about a recent work at ICML where we propose a new sparsity pattern to sparsify the neural network models ranging from smaller sizes to LLMs, as we show in the paper. And we also show how you can accelerate the training and inference of of the models having this particular sparsity pattern. So just to start off the presentation, the motivation behind sparse neural networks has been there, uh, which has been studied for a while. It's primarily the idea that you can reduce the number of flops that are required to do a say a forward pass without losing any accuracy. But on top of that, you also get training and inference acceleration. You get a reduction in the network size, which is good considering how large the current models are. And sometimes, interestingly, you also get better generalization and interpretability. In this talk, I'll be primarily focusing on weight sparsity. Activation sparsity and all other sorts of sparsities is something that we are looking at, but not in this work. The problem statement, so to formalize it a little bit, is to go from a dense network, or instead of having a dense network like the one showing on the left-hand side of the slide, we want to achieve, or we want to go to a sparse network which has fewer connections, as I'm showing on the right-hand side. And to put it a bit more formally, how can we train sparse neural networks without losing their algorithmic performance, which means accuracies or other software level or other application level metrics, and still accelerate the execution on the hardware? So that's our broad aim here. Sparsity, as we look at it, can be broadly classified in these two categories, where you have the unstructured sparsities, where your non-zeros are sort of present in the weight matrices in no particular order or no particular pattern. Whereas in the case of structured sparsity, your non-zeros are aligned in a specific or predetermined manner. The advantage with unstructured sparsity is that your accuracy of the model is most of the times closer to that of the dense model at low enough sparsities. And you can achieve higher level of sparsities as compared to higher level of overall model sparsity as compared to, say, something like structured sparsity. But the disadvantage that you have with unstructured sparsity is that you are not able to take the advantage of underlying sparsity in the model when trying to accelerate the computation on the hardware. Whereas when it comes to structured sparsity, the main advantage is the fact that you know where the non-zeros are in the model, or you can, given a particular non-zero value or a position of a non-zero value in the weight matrix, you can determine where other non-zero values are around that particular value. And that gives you the ability to accelerate the computation on hardware. The downside to structure sparsity is that in most cases, your accuracy won't be as high or close to that of a dense model or an unstructured model, specifically when you are trying to compress the model to higher levels of sparsities. So our aim with this particular work was to see if we can kind of get the best of both worlds here, which means that can we have a sparsity pattern that gives you similar accuracies to that of an unstructured sparsity and is hardware friendly at the same time. And this is where we propose our diagonal sparsity, which has non-zeros on these diagonals across the matrix. So which means that your non-zeros are not only present just on the main diagonal, but they are also present on these off diagonals as well. What you will notice here is that your diagonals, they are all of the same length. And that is because we allow the diagonals to sort of wrap around the weight matrix. We talk about this a little bit more in detail in the paper, but the intuition, or one of the intuitions behind kind of having this particular sparsity pattern, is its small world connectivity, which is desirable when it comes to efficient information processing throughout the network. And what I mean by small world connectivity is this sort of local clustering that you will see across the or around the main diagonal, and global connectivity, which is basically the ability, if you plot this in a ring manner, you will see that you can go from any node to any other node in few hops, like 1 or 2 hops, and that is what your global connectivity comes from. So if this makes sense, then the next sort of argument, or the next question that you have in mind, is how do you actually go about training a model like this? So given a network specification, which means number of layers, types of layers in a model, layer dimensions, and the overall sparsity budget, how do you go from that to a network which has diagonally sparse weight matrices, as I'm showing on the right hand side here? To do that in an end-to-end differentiable manner, you need to have a formulation, a matrix formulation, which formulates how to obtain diagonals in your weight matrices. So to understand this, let's just take a very simple example. Let's take an example of a matrix that has just one diagonal. So say the matrix looks like the one I'm showing here. To represent this matrix, we can break it down into two separate matrices. One which talks about, or which is responsible for the for ensure for which is responsible for dictating the position of the non-zeros, and the other one which is responsible for dictating the values that goes in the diagonals. So the position matrix is what we use permutation matrix for dictating the positions of the diagonals. The characteristic of a permutation matrix is the fact that in each row and column, you only have one non-zero, and with permutation matrices, that non-zero value is 1. Whereas for the value matrix, you just use a simple diagonal matrix where the values are on the main diagonals. And if you multiply both of these together, you will get the weight matrix on the left, which has the corresponding diagonal in the right position and with the right values. So if this is clear, then we can extend our formulation to a matrix which has, say, in this case, 8 diagonals. So all you need to do is have a position and value matrix pair for each diagonal. And you multiply those pairs together, and at the end, add them up to obtain the weight matrix on the left-hand side. And you can formally write this as I'm currently showing on the screen. So the next question is, okay, great, we have a matrix formulation with diagonals, but how do you actually obtain sparsity in this particular model, or in this particular weight matrix? So to do that, let's again go back to the formulation, and let's say we want a matrix that looks like the one on the left-hand side. So again, you will have a position value pair for each diagonal. And on top of that, what we do is we just introduce a factor, which we call in the paper as the importance factor, which dictates how important is a particular diagonal for the final diagonal matrix. And if the importance factor is 0, it means that that particular diagonal is not present in the final weight matrix. And if the alpha value is non-zero, it means that that particular diagonal is present in the final weight matrix. You can write this formally as I'm showing here on the screen. So this is similar to what we saw in the last few slides, with just adding another alpha vector to the formulation. So that's great. Now we have a formulation, and we can put this in a end-to-end training pipeline and obtain a matrix like the one showing on the right-hand side. The main parameters that you learn during training here are going to be your alpha values and your values in the vector V, which eventually turns into a value matrix. So these two will dictate the values on the diagonals, and it will also dictate which diagonals eventually show up in the final weight matrix of each layer in the model. Now the question is, how well actually does this perform? Before we go there, let's try to understand this particular formulation. What does that mean in terms of the training dynamics? Because there are two key things that we need to look at during the training to kind of ensure that it's working as you would like it to. So what I'm going to show you here on the left-hand side plot is on the x-axis, I'm on the y-axis, I'm plotting the number of non-zeros in the alpha vector. So if you remember this formulation that we have here, the number of non-zeros in the alpha vector actually dictates the total number of diagonals you will have in the weight matrix. And what this means is, if you provide if you have a sparsity budget, your training should adhere to that sparsity budget and eventually give you the required amount of sparsity. So the number of non-zeros in alpha will dictate that. So for example, in this case, we take a random intermediate layer, which is of size 768 by 768. I think this is from a ViT-based network. And we want a 90% sparsity in that particular layer, which roughly translates to having 77 diagonals in the weight matrix. So I'm gonna plot how the sparsity changes for during the training. So what we see is we divide our training in sort of two parts. One is an exploration phase, and the other one is just letting the model learn the weights. So in the exploration phase, what we do is we say to the model that, or we say to our training that, okay, we want 90% sparsity in this particular layer. So we see that the model or the training is in such a way that in that particular layer, it does not start with 77 diagonals. It rather starts with around, in this case, I think that number was around 176 diagonals. So it starts with a higher diagonal budget at the start of the training, and slowly and gradually, as it completes the exploration phase, it brings down the total number of diagonals to the required amount of sparsity. And once it has done that, there is very little variation in the total number of diagonals in the layer at the throughout the training. We have sort of more details in the paper about this, but we choose around 1/3 of the total training time as the exploration phase. We did try it with different values, and 1/3 was also the number that was used in the paper from Google a few years back, called rigging the lottery. So we found that for our method as well, 1/3 of the training kind of worked as a good empirical value for setting the exploration phase. So the takeaway that I would like you to go from this particular slide or this particular plot is the fact that even though we want a 90% sparsity, the training starts at a higher level, at a lower level of sparsity, and that, if you look at our results, seems to work good for such a training process. And second thing is, I think what is also interesting to understand is, if we are starting with higher number of diagonals, how does the model learn the positions of the diagonals during the training? And what I mean by that is it happening, or it's possible that the model just picks top 77, for example, diagonals at the start of the training, and it just sticks with those diagonals throughout the training, and it is not actually exploring those diagonals. So to kind of understand that and to ensure that's not happening, what I'm going to plot here is the Jacquard distance on the y-axis, and on the x-axis you have the iterations of training. So the reason for using Jacquard distance as a metric here is to kind of ensure that if you look at the alpha vector for a particular layer, which again dictates how many values or how many diagonals are there in the eventual weight matrix, and what are the chosen indexes of the diagonals. So what I'm doing here is I'm kind of trying to understand the alpha vector at iteration I and alpha vector at iteration I plus 1. So if they both are the same, then the Jacquard distance will be 0 between these two iterations. So the larger the distance, it means that they are they are not similar to each other. So if I plot that here, what we see is that at the start of the training, the training process is kind of going through a large number of diagonals to pick the top 77. So which means that uh, over the course of iterations, the distance is kind of reducing as it is closing down the exploration phase, which means that the training is kind of settling upon the top 77 diagonals at the end of the exploration phase. It starts off with high Jacquard distance, but it kind of lowers, or it goes closer to the 0 at the end of the exploration phase. And more interestingly, once that exploration phase is done, it has settled on those 77 diagonals, and it is just focusing on learning the weights of those diagonals instead of learning the positions as well. There's a lot more detail in the paper about how we do this, but the main idea was to kind of use a softmax function or a differentiable top k function to do this. Because if the function is differentiable, then throughout the training, it learns to pick the top k diagonals, and it can be included in the both forward and the backward pass. Okay, great. So to understand better or to actually see how well does this particular training process along with the sparsity pattern proposed performs, we compare this against a few baseline methods. So for unstructured sparsity comparisons, we use Wriggle, which we treat as sort of an upper bound in terms of the algorithmic performance that you can get. And for structure sparsity, we compare this against a pixelated butterfly, which is a work that came out of Stanford, I think a few years back. We compared it against block shuffle, which also has block sparsity. And then we compared it against S-Wriggle work, which came out in ICLR a couple of years back, I think 2 years back, and that has NSTM sparsity. We run the training on a few of those models, ranging from a very small MLP mixer model, which was around, MLP model, which is around less than 1 million parameters. And we go up to a ViT large model, which is 307 million parameters. In the paper, we have also trained this on a GPT-2 medium, which goes around 340 million parameters as well. And we do this for different varying levels of difficulty in terms of the data sets going from CIFAR10 to ImageNet. Okay, great. So let's look at, to start off with, the inference accuracy. And I'm plotting the accuracy on the y-axis here, and on the x-axis, I am plotting the sparsity of the layers that we are sparsifying. So if you look at Wriggle as a baseline, what we see is that actually, as the sparsity is increasing, we see a decrease in the performance or a decrease in the accuracy as compared to the dense model, which is something you would expect. But we also see a common phenomenon with the sparse models, which is that at some level of sparsity, in this case around 60 to 70% sparsity, you do get better performance than dense models in some cases. And we saw this, I think, for ViT base, and we saw this, I think, for ViT huge or ViT large as well. But when it goes to VID large, VID huge or GPT-2 small and medium, there we don't see such a performance. We don't see such a artifact, so to say. We also plot here the other baselines that we are comparing against. And if you look at our diagonal sparsity, it kind of sits at the top of all the structured sparsities and just below the unstructured sparsity case. More importantly, if you will look at sparsities around, say, 80–90%, we are kind of bridging the gap between the unstructured baseline and the structured baselines, which is kind of interesting because you do want to get closer to the baseline set by unstructured sparsity, which we consider as an upper bound. Great. The other results that we have are related to the inference speedup. So we take a particular model. In this case, it's a VIT based model, and we are comparing it. We are running it on an NVIDIA A100 GPU, and we see that for an end-to-end framework or for an end-to-end running time, wall clock time, we see that our DynaDiag work is achieving almost around 3 to 4x speed up as compared to other sparsity patterns, specifically at higher levels of sparsities. Similarly, during training, we also see that this work is actually we are getting closer, or we are getting much better training speed up as compared to other sparsity patterns out there. And the last plot is what we saw in the previous slide, showing how the sparsity pattern actually, how the accuracy changes as you go to higher levels of sparsities. There are more results in the paper. I didn't want to delve deeper into that, but yeah, you feel free to check that out as well. So if I have to kind of summarize the results or the main takeaways here, it's that with DynaDiag, you get similar to unstructured sparsities performance, but not at the cost of lower performance on the hardware. With DynaDiag, we also see that without diagonal sparsity and our custom kernels, you get you are able to accelerate both the inference and training. And the last takeaway is from the figure that we have in our paper. This is our main figure 1 of the paper, which shows that if you are plotting the speed up and the accuracy on a plot, and so the ideal spot is somewhere at the top right corner. DynaDiag is closest to that particular spot on this plot, and our aim is to kind of push that yellow dot that you have here further closer to the top right corner, and we have some cool work coming out regarding that. So yeah, thank you for listening, and please feel free to check out our articles and our code as well. I'm working on releasing that as soon as possible, and I would love to hear what your thoughts are on that. So thank you.